So hi everyone, I'll just briefly introduce myself. I'm Wissam Ghantous. I'm an assistant professor at UCF. My area of research is really in between number theory and cryptography, but specifically tackling elliptic curves and modular forms. So this talk today will be about all the number theoretic basics that you'll need to understand isogeny-based cryptography. So I have notes written down on my iPad here, and I'll go through them and then add some more detail. And if you ever have any questions, feel free to interrupt me as I'm explaining instead of waiting until the end. So let's begin. But I have the impression that most people here don't work on isogeny-based cryptography. Is that right? Okay, good. So this will be hopefully useful for everyone. So the first thing that we're going to cover here is, where is this? I have a pointer that I should be able to use, but now it's disappeared that we've connected it. Oh no. Okay, I can't find the pointer. That's fine. So the first topic we're going to talk about today will be elliptic curves. And basically, the setup is the following. So we're going to take a prime different from 2 and 3. The reason for this is that we're going to do some simplifications later, and we want to be able to divide by 2 and 3. So you don't want to have 2 and 3 being 0 in your group. So you want a field of size p to the e, where p is different from 2 and 3. So the elliptic curve, e over k, is defined as follows. It's just a smooth projective curve of genus 1 together with a distinguished k rational point. So this definition, if you don't do a lot of algebraic geometry, is very scary. So I'll give another definition that will be much simpler and hopefully less scary to everyone. So equivalently, we can write it the following way. So this is called the Weierstrass equation for our curve, and it's basically y squared equals to x cubed plus ax plus b. So technically this is supposed to look a bit bigger, but because p was not 2 and 3, I was able to simplify this and make it look a bit nicer. So I only have two variables here, a and b, to determine my elliptic curve. Okay. Maybe if I use this, can you see if I do this? Okay, I'll use this because the pointer is not working for some reason. Okay, so here we have this equation for the curve, and the other thing that we need is also saying that the discriminant is not 0. So this ensures that it's smooth. And we'll need this in a second, so keep that in mind. Together with a point at infinity, which we denote by this. So this is playing the role of 0. Okay, so I'll just say a remark. It was supposed to be this initial definition here working with a smooth projective curve, but we're able to work with this curve instead. Technically, we should be working with a projective version of this. So if you homogenize this polynomial, you get this one instead. And this is the most general way you can write it down. So I have all the coefficients and all the variables. It looks less nice, of course, than this one that I had here. So this is why it's nice to do the simplification. However, the advantage of using this projective version is that you don't have to worry about saying the point at infinity, because the point at infinity, you can just think of it as just being this. And when you deprojectivize, you divide by the last coordinate. So you do end up with a 1 over 0. So point at infinity is a good name for it. So it will make sense in another second as well when I draw a picture of this elliptic curve. So basically what you need to remember is it's given by this equation. And of course, this quantity here is not 0. So now that I have an elliptic curve, I'm going to start defining quantities related to it. So the J invariant of the elliptic curve, of the elliptic curve is defined the following way. So this is the definition for it. And because I'm dividing by the discriminant, I need to make sure it's not 0, but it shouldn't be 0 by definition here. Okay. So now that I have this elliptic curve, it was defined over field K. I can look at the potential solutions that this equation can have over other fields. So if you look at an extension L over K here, you could look at all the points that are in L instead of K and still satisfy your equation. So this is basically going to include more points now because you're allowing bigger fields. And you, of course, always want to include the point at infinity. So basically now we have, we call this EL to tell us that we're allowing the coefficients to lie in L instead of K. Any questions so far? Okay. So here's a question to test our knowledge. What is the size of this group here? Well, the set, because so far I've only said that it's a set. Okay, so I'll write down what this is supposed to be to help us. So this is basically all the point x and y in Fp cross Fp such that y squared equals to x cubed plus ax plus b. Okay. And of course, I have to add the point at infinity because I made a big deal out of this earlier. Okay, so of course, you're not going to have an actual answer because I didn't say what a was and what b was, but let's still try to guess. So an upper bound, of course, so how many values for x do I have? P, and for y as well. So for sure, you can't have more than p squared options, plus 1 for the point at infinity. So this is definitely a correct upper bound, but it's a terrible upper bound. So you notice as well, once you fix your choice of x, how many possible choices of y do you have? Exactly, because, or you might not have a solution, but at most you're going to have 2 because it's squared. So this is a slightly better version. So at most 2p plus 1. The plus 1 is for the point at infinity. So in actuality, the real value is actually not too far off. So the theorem is the following, is that the size of that group is p plus 1 plus some error term. And the error term is at most an absolute value 2 root p. And this has a name, it's called Hass's bound. Okay, that was just a little question to practice the definition of the elliptic curve. Okay, so now I'm just going to quickly check on time. Okay. So the major result about elliptic curves, which is something you see very early on after realizing what their definition is, the first major thing is that they're actually not just a set that is, a set that is defined using geometry, but it's also a group. So that's a really big deal because there's no reason a priori for why these points here should have a group structure, right? I just define some points that satisfy an equation. In general, they won't necessarily be a group. But I'm telling you, because this is an elliptic curve, it will actually be a group. And that's a big deal. So how do I actually say what the group operation is? So this is a little tricky. First, I'll draw what the elliptic curve looks like, just to explain a little bit. Okay, so let's say we have this plane. If you look at this equation, you can either use Wolfram alpha or you just think for a little bit and you realize that it has to look something like this. Okay, this is the case where you have 3 roots. You can have the case where you actually only have 1 root, and it would look something like this. And you only have 1 root here, and the other 2 would be complex conjugate to each other. Okay, so if I want to add points, I'm saying this is a group, so there should be a way to have an operation on 2 points and have 1 point as an output. So if I have 1 point here and then 1 point here, I need to add them and get a 3rd point somewhere on the curve. So the way to do this is the following. You do the following. So let's say I want to add P here and Q. What you do is you draw a line touching P and Q. It will have to touch the curve a 3rd time somewhere. So you take that 3rd point and then you reflect it with respect to the x-axis, and then you're going to get another point here. And this is going to be the final answer. So R is Q plus P. This is how you add points. So clearly when I draw this picture, it's very simple. If I were to ask you to write down what the answer is, you wouldn't just actually draw this and then use a ruler. You would basically use analytic geometry where you actually solve an equation and then you look at the slope of this line passing through P and Q. You just set up a system of equation and you solve what are the coordinates of R, and they'd look something like, first coordinate and then second coordinate. And you can just solve this. This is something you can ask a high school student to do if they're good. But I just want to emphasize one thing. So one key point, this is known as Bézout's theorem. Maybe I can highlight this. So Bézout's theorem here says that the number of points where these 2 curves intersect, so one of them is of degree 3, the other is of degree 1, is going to be 3. But there's just one key problem, is that this theorem only works when I'm working with the projective version of the elliptic curve. So now this is not the projective version. I'm using the affine version, where I'm basically having to say, oh, but there's the point at infinity every single time. So there might be an issue, but we can solve this issue easily by reminding ourselves that there's a point at infinity. So I'll do an example. It's actually really simple. So let's do the following. So I have here 2 points. I have P and Q, and I want to add them. So if you draw a line passing through P and Q, you realize that this line doesn't actually touch the curve at a 3rd point. That's because you're using the affine version of this curve. You're plotting it on a 2x2, on R2, instead of plotting it in a projective space. So you have to tell yourself that actually it is touching the curve at a 3rd point, which is the point at infinity. So that's just the way you get around this issue. Okay, so here P plus Q would give us the point at infinity, which I said earlier is actually 0. So in this case, p plus q equals 0. That means q is equal to negative p. Does that make sense so far? Okay, so we've seen that these elliptic curves are sets, but they're actually also groups. And they come from geometry, because I was drawing these curves. So they have two sides to them. Okay, the second section now is isogenies. So now that we've seen these elliptic curves, we're going to learn about the morphisms between them. So a morphism can mean different things depending on the scenario you're in. The easiest case is if you're just working with sets. A morphism between sets is just a function, because there's no structure to a set, it's just a set of things. So a morphism would just be a function. But now we're working with an elliptic curve. So these elliptic curves have two natures. There's the algebraic nature, because it's a group. GP stands for group here. But it has a geometric nature, because it's a curve. So a morphism of elliptic curve has to respect both the algebra and the geometry. The algebra is a group, so what's the morphism of groups? It's just a group homomorphism. So hopefully you all know what that means. But then a morphism of curves is a little more subtle, and basically it has to be a map that is both regular, sometimes people call it defined instead of regular, but I'm just using the word regular here, and rational. Rational means you can write it down as fractions. Fractions of polynomials. Regular means that you're not dividing by 0 without realizing it, essentially. Okay, so these are the two natures. So let's write down the definition. So here, a morphism of elliptic curves, we're going to call that an isogeny, is basically a regular rational map that it's also a group homomorphism. Very simple. This makes sense philosophically. And the consequence is that it has to send 0 to 0 because that's how group homomorphisms work. An equivalent definition I'll mention because if you look up this in other references, you might have a slightly different version, but they're equivalent, is you can say that it's a regular rational map such that it sends 0 to 0. It will have to be a group homomorphism as a consequence. I just prefer to present it this way because I feel like this is more satisfying. Okay. So now that we know what a morphism is, these isogenies between elliptic curves, let's dive deeper into these isogenies. So the first proposition, yes?
Could you please say again what regular is?
Oh yeah, so regular, basically these maps, they're rational maps, and so it's like a fraction of polynomials, but you're not working in Q, so you're working in these extensions of like FP modulo some polynomial. So you want to make sure that your denominator essentially is not a zero divisor. So it's just like a technical thing. Does that make sense? Okay, great. So now this proposition is the following. So regular rational maps are surjective or constant. So because isogenies have to also be regular rational maps, they're also surjective of constant. If they're constant and send 0 to 0, that means they must be 0 everywhere if they're constant. The other case is they're surjective. So this is convenient. These isogenies are either surjective, which is convenient if you want to apply the first isomorphism theorem, by the way. I'll get back to that in a second. Or they're 0. Some people exclude this case. They say that that's not an isogeny if it's 0. But I'm going to include that as an isogeny because that's going to be convenient when I define the endomorphism ring in a minute. So this is useful for the first isomorphism theorem. Okay. So here's a remark. So far, I didn't really mention this, but you should ask me. I said that these isogenies, you can write them down as fractions. But what are the coefficients that I'm allowing for these fractions, right? When I write it down as a rational map, what field is the coefficient allowed to be in, right? So technically, you might say, well, depends where your elliptic curve is. If E, right, if I have some isogeny phi from E to E prime, well, E might be defined over some, I don't know, FP, and E prime as well. Where's phi defined? What are the coefficients of phi? We will always, just to play it safe, allow phi to be in the biggest possible field that you can imagine, just to play it safe. In some cases, you won't want that. So I'll make sure to be precise if I ever change. But here, we're just going to allow it to be the FP bar. Okay. But that's a good thing to keep in mind because, these things are coefficients, so we have to say where they live. Okay. So now, if your isogeny is invertible, we're going to call that an isomorphism. So that makes sense. So an isomorphism it should be an invertible morphism. Okay. Now, a first nice result is that two elliptic curves are isomorphic. Here I'm putting it in between parentheses just because I want to make it extra clear, but technically I said it earlier. If I don't say anything, that means it's defined over k bar. So E and E2, E1 and E2, no matter where these are, when I say isomorphic, I mean I allow the isomorphism to be over k bar. They will be isomorphic if and only if their J invariants are the same. So if I give you two curves and I ask you to check if they're isomorphic over the k bar, you just check the J invariance, and I'll remind you what the J invariant is. We have to scroll all the way to the top, and it's this following quantity. So that's an easy quantity to compute. And you'll know if they're isomorphic or not. Okay, this is where we were. So now, let's have the following thought experiment. So I give you an isogeny, and it's non-constant because I don't want it to be 0. That would be silly. Yes. Yeah.
About the curve morphism versus the group.
Yes.
So, like, okay, what I can think about, for example, an affine map, which is curve morphism that's not a group. Is there like some other example?
Well, technically, you can have something maybe that goes just to not 0, and it won't be a group homomorphism just because it's not sending 0 to 0. But that's not a very satisfying answer. I think there are more examples, just not something that I can just write down right now. But I think there's probably a ton of examples on Stack Exchange. So yeah, but that's a good question. I think anyone should have a look. You know, what's an example of a map that is, for example, maybe a homomorphism but not an isogeny, or a regular rational map that's also not an isogeny. Yes, I think you had a question.
Oh, yeah, I was just going to ask if I'm remembering correctly, the characteristic 0 are regular matched polynomials.
Yes, because you're not worried about dividing by 0. Yeah. Someone else? Oh, was that the same question? Okay, great. Perfect. Okay, so here's what I was saying. If you take a non-constant isogeny, it has to be surjective. So if you apply the first isomorphism theorem, you get the following. So E prime is just isomorphic to E modulo the kernel. So the isogeny just, we get the kernel out of this. But now if you do the converse direction, if you just choose a subgroup, C in E, and then you look, that means there must be an elliptic curve E prime, unique up to isomorphism, and some isogeny phi from E to E prime, such that the kernel is equal to C. So basically, let me go back to the first example I gave here. Here, I just had an isogeny, and I noticed that E prime, which was the target curve, is isomorphic to E modulo the kernel, which is a subgroup. If I start with a subgroup, and I try to essentially create E modulo that subgroup, there must be a curve that is equal to E modulo C. So you can kind of have both versions. So this tells us that these isogenies, you know, the kernel and the isogeny are essentially two sides of the same thing. Okay, so here's another info about isogenies. There's a lot of stuff that we're trying to cover, so another fact, yes?
Just to make sure I understand the setup. So when you say the portion there, E over C.
Yes, okay, that's a very good point. Let me be precise. This is a symbol. This is technically, I have to be careful here. So if E, you write it down as a group, and then you write C down as a group, then sure, this is a group. Sorry, C is a subgroup, so this thing is going to be a group. But that's not necessarily an elliptic curve. There is an elliptic curve E prime that is isomorphic to that. Is that what you were asking about?
So do you mean that there exists an elliptic curve for which the associated groups are isomorphic?
So there exists an elliptic curve E prime such that it is isomorphic to E modulo C.
But I guess I'm trying to understand what isomorphic
As groups.
curves are.
So basically this is an elliptic curve, and it's also a group because it's an elliptic curve. That's just a group. Doesn't have to be an elliptic curve. This is an abusive notation here. So let me erase a lot of what I've written here. So basically, the idea is if you start with E and then you take C inside of it, you want to be able to say E modulo C is an elliptic curve. This is what you want. But that's not necessarily always the case. But there is an elliptic curve that is isomorphic to it. So we always do this abusive notation and we say, okay, you take a subgroup and then look at E modulo that subgroup. That's an elliptic curve. And the isogeny that goes from E to E modulo C is just reduction modulo C. But of course, that's not actually reduction modulo C because that's an abusive notation. There is another curve, E prime, that is isomorphic to this, and there is an isogeny here. Does this make sense? Maybe can you ask your question again, because maybe I'm not answering it.
No, I'm just trying to understand what isomorphic elliptic curve. So do you mean that there exists an bijective P that does that?
Maybe I misspoke. Phi is only an isogeny.
So it does not make them isomorphic.
Yes.
So
If I said isomorphic, I misspoke.
no, you did not.
Okay.
Just to clarify that. So.
Oh yeah, this is isogeny.
So you have E over C. I understand that as a group.
Yes.
I don't understand that as a.
It's not a curve.
It's not a curve.
No, exactly. This is a very subtle point, and many people don't know that or choose not to worry about it. But technically, it's not a curve. But that's fine because there is a curve that is isomorphic to it as a group. That's a very subtle.
Isomorphic as a group.
Yes. Yeah, that's actually a very subtle point. And if you guys know that's very good. It's definitely not something that you should worry about at first. Okay, so here's a fact. In isogeny, we can write it down as fractions, but there's a standard way that you can write it down that will be very convenient for us. So you can always write it down this way. We have the first component just depending on x, and then the second one times y. If you write it down in the standard form, then I can define the following two quantities. Of course, I can define the following two quantities irregardless of how you write down your isogeny. This definition of degree can be defined without looking at this, but it's a bit more complicated, and I don't want to talk about like field extensions generated by isogenies. So it's much easier for me to define the degree based on the standard form here. So if you write down the standard form, you just look at this max of the degree of u and v, and that's just the degree of phi. So it's very easy to write down. It's a bit less easy for me to justify why the degree is multiplicative. To justify it, I have to use a complicated definition of the degree, which I didn't do, but you have to take my word for this. And it should make sense that the degree is multiplicative. So the degree of phi times composed with psi is just the degree of phi times the degree of psi. Okay? Moreover, we're going to have this extra word here, separable. So an isogeny is separable if u over v prime, the derivative is not zero. So this is just a technical assumption. You will almost never have to deal about non-separable isogenies. It will always be separable in most applications. Okay. So if the isogeny is separable, then it's very convenient because the degree of the isogeny is equal to the size of the kernel. So that's very nice. If you want to know the degree, you just see how big the kernel is. And now, here's the reason why I said you usually will not deal with non-separable isogenies. It's because of the following. If you have an isogeny, you can always decompose it this way. So you have this part, which I guess we call the separable part. And this part here is just a Frobenius endomorphism. So the degree of the Frobenius endomorphism is going to be p. So if this has degree p to the r, and this is something that doesn't have p in it, then this is going to have a degree, okay, let me say that again. If p doesn't divide the degree, that means there can't be any part of it that's Frobenius, because that brings a component p. So the isogeny will be separable. In practice, the degree of the isogeny that you'll look at will never be divisible by p in most examples that you'll see next Friday with JF. So most isogenies you'll be dealing with in practice will be separable. And that's very convenient because then you know that the size of the kernel is the degree of the isogeny. Perfect. Okay, a few more definitions, but then they come with examples. The first one is the endomorphism ring. And you might say, okay, well, that's just a basic thing. It's just isogenies from an elliptic curve to itself. But this will be extremely useful. So we're going to look back at endomorphisms again and again in the next pages. Okay, and then automorphism ring is just endomorphisms that are invertible. Ooh. Okay, so let's do an example. if I ask you to think of an endomorphism, of course you could just give me the identity map. That's a silly example. A slightly less silly example is the following one. So this isogeny sends xy to x minus y. And why does this work? Let me remind you what an elliptic curve looks like. You have y squared equals x cubed plus ax plus b. What happens if you replace y by negative y? It doesn't change anything because there's a square. So you go from the curve to itself. So that's why it's an endomorphism. Why is it an automorphism? Well, if you do it twice, you go back to where you were. So it's its own inverse. So it is invertible. So that's why it's an automorphism. Does that make sense? Mm-hmm. And why do I call it -1? That's just the name, right? That's just the name for it. This name will make sense in a minute, but we just choose to call it that. In practice, if you add a point, this will correspond to -1 in a very meaningful way. Okay. So, how big can the automorphism group be? Well, we know exactly how big it is. I haven't written it down because it depends on some cases, but I wrote down something similar. So, if J invariant of your elliptic curve is not 0 and it's not 1728, then the automorphism group is just these two examples, the identity and -1 that I just mentioned. So there's nothing else. So it's very convenient. You know exactly that there's only two elements. There's cases where you have more, but the cases where you have more are precisely 0 and 1728, in which cases you have 4 and 6. Okay, so now you can take a point on an elliptic curve and add it to itself m times. We call that the endomorphism square bracket m. Yes? Yes. So let's scroll all the way back to the top. So let's go here. This one. So this is the J invariant. We call that J of E, and it's defined this way. So you have -1728 times 4a cubed divided by the discriminant, which is here. So it's a quantity associated to your elliptic curve. So you can either think of it as just some fraction that is meaningful, depending on your coefficients. But you do know that deep down, this tells you if your elliptic curves are isomorphic or not. Let me find it. Here. So two elliptic curves are isomorphic if and only if their J invariants are the same. So the J invariant conveys a lot of information. Well, maybe not a lot, but it conveys some information at least. And here, turns out that if you avoid 0 and you avoid 1728, then the automorphism group is perfectly of size 2. So these are, in some sense, I think of them as troublemakers because they kind of cause some issues at some point. But the issues are not that big of a deal. Okay, does that answer? Perfect. So now I was saying that you can, for every integer m, you can think of it as an endomorphism. So we have a map from Z to the endomorphism ring of E. And once I show you, this map is injective. And once I show you this, you might ask, okay, so the endomorphism ring contains Z, but is it equal to Z or is there more stuff in there? So how big can this endomorphism ring be? So I think you might already be able to tell me if it's equal to Z or not. If you can think of an endomorphism that's not Z, then it's definitely not equal. And an easy example is there's the Frobenius endomorphism, which sends xy to xp, yp. And that's not in Z. So it's definitely not true. So there's at least more. So there's always something more. How much more depends. Okay, let me check the time. We're not doing too bad. So if P now, I was talking about how the endomorphism ring is bigger than just Z. I'll give more information on how big it is in a few pages. So now let's look at this thing. It's EM. So this is basically defined as the kernel of this map. This is all the points that if you take them and add them to themselves m times, then you get 0. So what is this? Well, if I'm assuming if P doesn't divide M, because again, P is the problematic case here. If P doesn't divide M, then we know that it's basically M cross, Z cross M, Z mod M cross Z mod M. Okay, I'll use that in a few pages, so also keep that in mind. But now, okay, this is when P doesn't divide your integer, but what if it divides it? Well, if you have P to the power E, then it's either 0 or z mod p to the power ez. And here I say for all e, so this never changes. So if you take e to be 1, for example, let's say you take e to be 1 and you realize that you're in this case, and then you take e to be 2, you will have to still be in this case. It can't alternate. It will always either be here or always be here. It can't switch after, it can't change when you vary e. But we will again focus on this one. This is the one that we will be in because we don't want to be divisible by p for the examples that we'll see in the future. Okay, so we're almost done with isogenies. One last thing. When you have an isogeny, it's a map that takes you from e to e prime. There's always a way to go back. So there's always an isogeny which we call the dual, which takes you back from e prime to e. And it's not just a way to go back. We know that if you compose this with this, you just get the degree. So for example, if the degree of phi is, 3, then if you compose phi dual with phi, then you just get multiplication by 3. So I just want to emphasize something so we can maybe notice an interesting thing here. What is the domain of this map here? I didn't hear. No, the domain, so one of those. Right, so it's E prime. And what's the domain of this? It's E. So this equal sign is doing a lot of heavy lifting here because they're not literally equal because they have different domains. So they can't be the same map if they have different domains, but they're equal in the sense that they're both multiplication by the degree. So this map here, when I say multiplication by m, it's an endomorphism. It doesn't matter what your domain is. It's just always going to multiply by m. So, it's kind of blind to the domain, but I'm just emphasizing that saying that they're equal here is kind of slightly misleading, but it's not a big deal. Okay. Let's do an example. So this one I just copied from a computer because writing it by hand is a futile exercise because these things usually don't do by hand. But basically, let's start with the following elliptic curve. So this is the case where a is 0 and b is 1. So this elliptic curve has j invariant, either 0 or 1728, which you might say is one of these annoying ones, but we're not going to get to the point where this annoys us. We're just going to use it as for a way for me to illustrate that you can write down indeed an isogeny as a rational map like this. So this isogeny, which is multiplication by 2, takes a point p to p plus b. So this isogeny, you can write it down this way. This way, I would say, is a very algebraic way. I'm using the group property, just p plus b. This here is more, I guess, a geometric way, using the geometry of the curve itself. So this is useful if you want to think about it conceptually. This is useful if you want to do it on a computer. Yes?
That's the question. Geometrically, algebraically, but geometrically, what does it mean to add itself on the curve? Like, how do you...
That's a very good question, because essentially this is one of those things where like the elliptic curve, you can tell yourself it's a group and then not worry about the rest. But you want to remind yourself that actually this is how you are adding points. You really are doing this every single time. Oh, I see what your question is. You're saying how are you adding a point to itself? Okay, let me answer this question. It's actually satisfying to see. So here, what I'm doing is the following. So let's say this is my elliptic curve. I hope that the way I drew the example does, oh, wait, okay. I need to be careful to draw it in a way where I can actually, okay, maybe this is good enough. So let's say this is P, okay? Sometimes if you draw it bad, your example fails because of the fact that you can't draw well. So hopefully this is not gonna be one of those. So if I wanna draw a line that touches this curve at P and P again, it will be the tangent line. So this is why I was trying to draw it careful, so you can see that there's a third intersection here. So then this would be 2p. Of course, you have cases where, like, let's say it looks like this, and then this is p. Then this p plus p would be the point at infinity. So if p plus p is equal to the point at infinity, this tells us that p equals to minus itself. Okay. So does that make sense? Yeah, that was actually a very good question. P plus p is 2p.
We have to take projection.
If you project the point at infinity, yeah, good point. Yes. Let's fix, that's a very good observation. Thanks for noticing that. Let's fix it like this. Very good. So this is indeed 2p in this case. Here, you're right, I should project the point at infinity, but if I project it, I still keep the point at infinity. Very good. Okay. Someone else had a question? Okay, very good. Let's keep going. Okay, well, what is the kernel of this map? We know that the kernel is basically all the points such that if you add them to themselves twice, you get 0. We called it this. It's just notation. Well, you definitely have 0 in there. You also have this. These two you can check with a computer. Okay, and then it is indeed equal to z mod z cross z mod 2z. You can see that if you add, that this has that structure. Okay. I will emphasize this proposition here. It's saying the following. If you have an isogeny of degree, let's say 8, well, you can break it down as 3 consecutive isogenies of degree 2. So if you have, let's say here, e all the way to e prime, and this has degree 8, you can break it down a smaller step, each one of like degree 2. This is useful for actually coding on a computer. So next week, when JF is going to present an actual crypto scheme based on this, he's going to say like an isogeny of degree 2 to the something. But once you actually code this, you're not going to compute an isogeny of degree, I don't know, 128. You're going to, let's say 1024. You're going to compute 10 isogenies of degree 2 back to back, which is easier. Does that make sense? Okay. Okay, so here's a question. How many isogenies are there? So this is a question that will allow us to practice our knowledge. So how many isogenies are there of degree precisely L? Here L is a prime that is co-prime to P for convenience, coming out of E. So the number of isogenies coming out of E of degree L, well, by the way, L is co-prime to P, so these isogenies are separable. So the size of the degree of the isogeny is equal to what? It's equal to the size of the kernel. So the question is, how many kernels are there of size L? Right? The kernel is a subgroup. So I'm asking, essentially, how many subgroups are there in E of size L? Well, it's the same thing as saying the number of, well, if it's a subgroup of size L and L is a prime, it's cyclic with a generator. So I can write it this way. So subgroups like this, generated by some P, where P has the right order. But I can also write it this way. It's, if I just look at P, I also have to mod out by the fact that different points might give me the same subgroup. So basically, if I have 2 points that generate the same subgroup, then I'm going to consider them as equivalent. So finally, the answer becomes, oh, by the way, what is that set here? The number of elements of order L. So if you allow the order to be at most L, what do you get? You get this thing here. Z cross L, sorry, Z mod L cross Z mod L. Right, because I was saying earlier that this thing is equal to Z mod M cross Z mod M. So here I have L. Technically this is order, so it's not the same as this, but we can include up to L. So if I ask you the question, if you, how many elements in Z mod L cross Z mod L are there if you want to see that they generate a group of size L, modulo generating the same group? The answer is going to be, well, it's going to be L plus 1 if you just count how many points there are and remove 0 and divide by the possible, them being equivalent, and then again remove 0. This is one of those things that's not too tricky to do by hand, but it might just take an extra minute to explain. And I'm just going to keep going unless you really want to see the details. But what you really should know, at the end of the day, the number of isogenies of degree 2 is just 3. And the number of isogenies of degree 3 is 4. It's always L plus 1. Okay. So now let's get back to this question that I asked a few pages ago. This endomorphism ring is not equal to Z, but like how much bigger is it? Here's something. So if we look at the endomorphism ring, and it's inside a quaternion algebra, then we say that our curve is supersingular. So this sounds a bit confusing, so let me explain something. The endomorphism ring of E can be one of two things. It can be either an quaternion algebra. Quaternion algebra is like this, exactly this, right? You know the quaternions. Okay, but then it doesn't have to be. It can be in some quadratic extension. Yeah. So I don't know, like just QI, for example. It won't be QI, but that's an example of a quadratic extension. So it's one of those. This has dimension 2 over Q. This has dimension 4. It's going to be in one of those two. If it's in the case of dimension 4, in other words, if the endomorphism ring is in our quaternion algebra, we say that the elliptic curve is supersingular. This is a very fancy word, but what you need to know is it just means that the endomorphism ring is one of the biggest cases possible. Okay, so to make it extra clear, so here's the usual quaternion algebra, Q, and then you have I and J, and I times J is equal to minus J times I. What's an example of an order in a quaternion algebra? Well, that's, ooh, I want to erase. The easiest example is you just have, it's a lattice in your quaternion algebra. So you just replace Q by Z, for example, and then you get this. This is the easiest example. Okay. Now, if you have a supersingular elliptic curve, let's say it's defined over FP bar. That's the most generous definition you can allow. You're allowing your elliptic curve to have coefficients in this huge field extension. Turns out that there's another one, only defined over FP squared, that is isomorphic. So remember, we only care about up to isomorphism. That's always, like in most algebra, you only care about things up to isomorphism. So because there's always going to be an example that's isomorphic and over FP squared, from now on, we will always allow our elliptic curves that are supersingular. We're going to assume that they're over FP squared because there's always an equivalent one over FP squared. Why is that practical? Why is that useful for like actual applications in cryptography? Well, remember, if you want to write down your elliptic curve, you have to tell me what A and B are. And if A and B are in there, good luck writing that on a computer. And you know, if they can change that, you know, this is going to be a nightmare. But if actually they're in there, that's manageable. Okay, so how many supersingular elliptic curves you can have? Well, we know that they're in there, so it's at most P squared, but actually we know that there's about P over 12 of them. Okay, I'm going to speed up a tiny bit, but I don't want to lose anyone, so let me know if I speed up too much. There's a very important correspondence that we can make.
So what about isomorphism?
If you have an isomorphism between two elliptic curves, they have to either both be supersingular or none of them are supersingular. Is that what you meant? Oh, you meant... This was all isomorphism classes. Oh. Sorry, this is a bad word. There's infinitely many. But here I mean up to isomorphism. Up to isomorphism. All of this is up to isomorphism. Thanks for pointing that out. I meant up to isomorphism because you can have a lot more just in general. Okay, so the During correspondence. let me do the following thought experiment, I guess. So we have this thing, BP. BP is basically a quaternion algebra. It's the only quaternion algebra that ramifies at Pn infinity. What does it mean to ramify at Pn infinity? It means that if you take B, tensor it to go from Q to QP, QP is the p-adic numbers, then this is a division ring. What's a division ring? It's a ring where non-zero elements are invertible. So what do I mean by zero elements? Okay, yes. So you don't have to worry too much about this, but just think of BP as being a very special quaternion algebra. So it's going to look like this: Q, QA, QB, QAB, and AB is equal to minus BA. And every time I said A and B, I meant alpha and beta. I just misspoke. Okay. So here we have this special quaternion algebra, and here's a few definitions. An order, O, in my quaternion algebra is a lattice that is also a subring. So it's basically, the easiest example is you take this and you replace all the Q's by Z's. Okay. And then what's a maximal order? Well, it's an order that is maximal in the sense that there's nothing bigger in it, except the whole thing itself. So it's an order that's the biggest with respect to, it's maximal with respect to inclusion. Okay, now that you have an order, what is a left ideal? It's an ideal, but multiplication from the left. So a left ideal I of your order, it has to be a lattice. Everything here is a lattice, such that if you multiply from the left, it doesn't change anything. So it is an ideal in some sense. It's also a lattice. Okay, given a left ideal, you can take the right order of your left ideal. Because here I was saying if you multiply from the left, then you're not in I anymore. But you can take all the elements such that if you multiply from the right, they keep you in I. This will be an order again. So I know this is a lot of definitions, but let's do the following experiment and see what happens. So take your maximal order, take any maximal order that you want in BP. So you have your maximal order O. So the second thing you do, you look at all the left ideals of O. We're going to call this LO. L is for left and O is for O. Take all the left ideals. The first one is just going to be O itself, and then you have a few others. N here is going to happen to be the same number of, is going to be equal to about P over 12, the number of supersingular elliptic curves. That's not a coincidence. Okay, so you take a maximal order, you take all the left ideals, then you take all the right orders of the left ideals. So you take O right of every one of them. Okay. This list that I have here is exactly equal to the endomorphism ring of every single elliptic curve. It gives you all of them. So this hints to the following correspondence that we have. There's a correspondence between supersingular elliptic curve over FP squared and maximal order in BP. And this, you might say, okay, well, that seems abstract, interesting for algebraists, but maybe not useful in practice. It will be extremely useful in practice. So here, elliptic curves correspond to orders. Isogenies correspond to left O ideals. Here, this is the ideal corresponding to the isogeny phi. I wrote down the definition. There's an actual concrete way of saying what it is, and I won't spend more time on this so I can cover everything. So there's a correspondent that gives you a way to go between the world of elliptic curves to the world of quaternion algebras. I'll say a few more things very quickly. There's a special algorithm called KLPT. This is very important. It does the following. It takes as input an ideal and outputs an equivalent ideal of a certain norm. So this ideal is going to correspond to an isogeny. It's going to give me another equivalent ideal, which is going to be another isogeny, same domain, same codomain, but of a given norm. So you can go from one isogeny to another isogeny of a different norm using this algorithm. And this is going to be very useful, again, for applications. Hopefully JF is going to cover this. Okay. I said that the endomorphism ring of E is in a quaternion algebra. So you remember the quaternions, we have ij equals negative ji, right? So it's not commutative. So this end E here is not commutative. But maybe we can do something that will be commutative. What if I do this end E, but then I have a subscript FP? This means I take all the endomorphisms as long as they're defined over FP. Before, I said that my endomorphisms could be defined over FP bar, and it gave me something non-commutative. Now, if I say it has to be coefficients in FP, this is going to be commutative again, because it's not in a quaternion algebra anymore. It's going to be in a quadratic extension of Q. So it's commutative again. And why is that useful? It's useful because we get a group action. I'll say what the group action is in a second. So here, we always have Z inside the endomorphism ring. I made a big deal out of this before. But also we have Frobenius. So we always at least have this. There might be a bit more, but we always have at least this. Okay. So now let me call O the endomorphism ring over FP. It's important that it's over FP, so that makes it commutative. If I have an ideal, you can always write it. Actually, let me skip this because we're almost out of time. If you have an ideal, I can write it down. I can write an isogeny that corresponds to that ideal. And you're saying, well, you just explained that earlier, that ideals correspond to isogeny. I did. I'm doing it again in this case. So how do I do this? Well, our ideal, you can write it down as two parts. The first part contains Frobenius. The other part doesn't. The S here stands for separable, because before I was saying that any isogeny has a separable part and a Frobenius part. So that's actually very good naming. I mean that this matches perfectly to what we had before, which makes sense because ideals do correspond to isogenies here. Okay, so given that isogeny, given an ideal A, what is phi A gonna be? So it's gonna take me from E to E modulo A. So E modulo A, that's easy, it's just the image of phi. So what actually matters, I gotta tell you what phi is. Phi is an isogeny, so it has two parts. It has a non-separable part and a separable part. So the non-separable part is just Frobenius to the power r, where r is this thing here. The separable parts, to define it, I need to tell you what the kernel is, because again, separable isogenies are given by their kernel. The kernel is this. So everything can be written down explicitly. And I know I'm not spending too much time on all the details because there's so much to cover, but I'm hoping what you need to remember is that there's a very explicit, convenient way to move between the world of isogenies and the world of ideals. Conversely, given an isogeny, you can get an ideal, and it has a way of writing it down. Why is this a big deal? Oh, also, I'll say it again. An isogeny composition corresponds to ideal multiplication. Endomorphisms are isogenies going from a place to itself. They're going to correspond to principal ideals. So we have a very clear correspondence. So why was I explaining this here? Let's take the following. L, F, P, O, pi, that's going to be this notation that I have for all the elliptic curves over Fp, such that their endomorphism ring corresponds to O. Here, O should be in a quadratic extension. So this is commutative. If I have this, I was telling you earlier that I can turn an ideal into an isogeny. So how is an ideal going to act on an elliptic curve? You know how an isogeny acts on an elliptic curve. You just apply it to the elliptic curve. The ideal is going to act the same way the isogeny does. So if I had, for example, phi from E to E prime, no one in their right mind would think of this as a group action. It's just an isogeny going from E to E prime. But turns out it's a good way to think of it as phi takes in an elliptic curve E and outputs an elliptic curve E prime. Because if you write it in the language of ideals instead of in the language of isogenies, you have this ideal here, A. If it acts on an elliptic curve, it gives us the elliptic curve E mod A, which is essentially the output of an isogeny. Why is this useful? Well, you have a group action. You can do cryptographic stuff with group actions, and this is commutative. So you have a commutative group action, you can do Diffie-Hellman, but I'm not going to spend time on this because this is something that JF is going to do next week. One last topic, which is my favorite topic, which I'm going to cover very briefly. You can have a graph out of these elliptic curves. So the vertices of my graph, they're going to be E, where E is SS stands for supersingular, elliptic curve over FP bar up to isomorphism. What are the edges? For every subgroup of order L, you draw an edge from E to E mod C. When I say E mod C, someone was asking earlier, I don't actually mean, E mod C is technically not an elliptic curve, but we view it as an elliptic curve because there is an elliptic curve that is isomorphic to it. Okay, so let me say it again, but in a slightly different language. So the vertices are going to be the supersingular J invariants that correspond to my elliptic curve, because every elliptic curve can be viewed by its J invariant. And they're up to, if you view them up to isomorphism. And then the edges, I think this way of writing it down is a bit easier to see. It's an isogeny of degree L. So the edges are just isogenies, but there's a slight equivalence here that I have to say. An isogeny is the same as composing with an automorphism. Why is that not too much of a big deal? Well, earlier I was saying that an automorphism is just plus or minus 1, if you're not 0 or 1728. So this is not a big equivalence class that you have here. Okay, so isogenies are essentially, the edges are essentially isogenies of degree L. Okay, so this is a graph. Here are the properties of the graph. It's a very nice graph. So we know how many vertices it has. I said that the number of supersingular elliptic curves is basically p minus 1 over 12. I even told you what the epsilon was earlier, but I didn't write it again here. The graph is sparse. That means that if you look at the whole number of vertices versus the whole number of edges, there's a big gap between them. If you want to say that rigorously, you can say that the adjacency matrix, the number of entries in the adjacency matrix is logarithmic with respect to the size. But I prefer to say it in English and just say that if you look at it from far away, you can see a lot of gaps in between the edges. The graph is regular because I made a big deal earlier out of saying that every elliptic curve has L+1 isogenies coming out of it, no matter what elliptic curve. So every point you pick on your graph, every vertex has L+1 edges coming out of it. Okay, let's skip this one for a second. It has very few loops and multi-edges. And then for every isogeny, there's a dual isogeny. So for every outgoing edge, there's an ingoing edge. So you can always have a way to go back. So people kind of think of this as being an undirected graph. Now I'm going to say one last thing, and I'll let everyone go after this because we're almost out of time. I was told I could use the full hour. So these graphs are optimal expanders. What does that mean? So I'll say it in English first, and I'll write down the theorem. So let's say you can live for a very long time, and you don't need to eat, and you don't need to drink water, and you don't need to sleep. And I just send you, and you keep walking randomly. So you take a step in one way, and then take a step in another way. And I wait 100 years, and I come back. You will still be on the American continent because you don't know how to swim, right? There's no way you can end up in Europe. That's not something that happens for isogeny graphs. If you start walking around, and I come back after a little bit, you could end up anywhere. There's nothing that stops you from ending up in certain locations. So in the previous example I give, with like a big probability, I know you're still in America. But for isogeny graphs, you can end up anywhere with the same probability. So here is the statement. So let's do the following random walk. You start on your favorite vertex, V1. V1 is just some starting point. It could be any starting point on your graph. Every time you take a step to the next vertex. So you go from V1 to V2 randomly, V2 to V3 randomly. After k step, Vk is basically the kth step after starting at V1. And V, this probability here, this probability is over the variable V. V so this probability is over V in the vertex set of our graph. Okay, so the probability after k steps of ending at vertex V is 1 over n. 1 over n is the uniform distribution, right? There's n vertices. 1 over n is basically the probability of choosing a vertex at random. We want this ideally to be 0. That means this is literally, you could be anywhere, literally. Of course, that's not true because this is an actual construction here, but this is going to be very small. So epsilon here is very small. So if you take a random walk on this graph, you could end up literally anywhere. And this is going to be equal to the uniform distribution. And the really important step here, which I haven't emphasized so far, is that you don't even have to wait for so long. You can end up anywhere after a short amount of time because you see a log here. So if I write it slightly nicely, instead of if I plug in epsilon to be 1 over 2, actually, there's a way to make this cake explicit. So let me use the final result directly. So here, let's say n is log base 2 of 2n. After k steps bigger than log base 2 of 2n, this is basically similar to log of p. You can end up anywhere with this error term. And n is really big, so this is a very small error term. And this is where I'm going to end. So this graph is a mixing graph. So any questions about this? Perfect. That's the end.